Today I'm going to introduce you to logarithmic functions, and we abbreviate logs with so it's logarithmic functions. This is the title of the lesson. And we're going to learn what are logs today and when can we use them. So we're going to start off with what you are comfortable with, and we're going to start by thinking about inverse functions. So let's go with something like this. Now if we go back here, let's just come over off to the side, let's just do a quick review. In Algebra 1-2, you learned how to find the inverse of a function. We reviewed it again this year, and remember procedurally what we do is we switch the x and y, and then we solve for y by doing the opposite operations. So opposite of adding 6 is subtracting 6. Oops, excuse me, this can't cancel. Whatever you do to one side, you must do to the other side. Opposite of multiplying is dividing. Again, whatever you do to one side, you must do to the other side. The 3 must be shared with both the x and with the 6, and it reduces to look like this. This is the inverse. But really, we talked about a couple weeks ago, what does that mean? So if I plug in numbers for the input, what do I get for the output? Let's try a few of these. If I plug in a 2, 3 times 2 is 6, 6 plus 6 is 12. So 2 maps onto 12. Let's try an easy one like 0. If I plug in 0, 3 times 0 is 0, 0 plus 6 is 6. Now, if this is correct, if this is the inverse of this original function, it's going to be able to map backwards. So 12 will map to 2, and 6 will map to 0. Let's check. 12 divided by 3 is 4, 4 minus 2 is 2. 6 divided by 3 is 2, 2 minus 2 is 0. That's the concept of inverse functions. Now let's apply that same concept. Instead of doing a linear function, we're going to do an exponential function. So let's break it down here. Let's start with 0. Could I do negatives? Sure I could, but they would turn into fractions, so I'm going to try to keep it easy. Remember, any number raised to the 0 power is 1. It's not 0. Any number raised to the 0 power is 1. 2 to the first is 2. 2 to the second is 4, to the third is 8, to the fourth is 16, and so on. So when I do the inverse of this, as we've spoke about previously, the domain and range are going to swap places. So wherever the x's were here, they become the y's in the inverse. So 0, 1, 2, 3, and 4, and corresponding 1, 2, 4, 8, and 16. So I want to find an equation or create an equation that when I plug in 1, I get 0, I plug in 2, I get 1, and so on. So how do we do that? So I'm introducing logs to you right now. Logs are simply another way to represent exponents. But the real reason we learn logs, and that is true, but the real reason we learn logs is whenever we have to solve an equation and the variable is in the exponent position, we can't do it without logs. That's the only reason we truly have to learn logs. Once again, if I'd be solving for x and the x is in the variable position, that's the reason we learn logs. So at this time, I'm going to find the inverse to see, does it work? If I find the inverse and I substitute in these input values, do I get these output values? So the first thing is I switch the x and y, just as I did up above. Okay, now my goal is to isolate this y. So to do that, I need to get rid of the 2. And so I'm going to write the log on both sides. Log is abbreviation for logarithmic. And whatever number I'm trying to get rid of is the base of that. Remember, just like up above here, whenever I did something to the right, I must do it to the left, and vice versa. Right must do it to the left. So over here, if I do the log of 2, I must do it also to the left-hand side. Now, why did I choose base 2? Because I'm trying to get rid of 2. So I'm going to write everything else down. Okay, now I'm going to simplify. We're going to kind of dive into this a little deeper later today, but this portion right here that I'm just putting little dots around, it simplifies to 1. I'm going to explain that in just a second. So this simplifies to a 1, and then I get to bring down whatever the exponent is. So 1 times y is the same as y, and now I've isolated the y. And I believe this is the inverse of this original function. Okay, so how can we check? Because we don't know how to evaluate them yet. Well, we're going to jump over to, hold tight here, and we're going to jump over to the Desmos graphing calculator, and I'm going to type in the original, which is y equals 2 raised to the x power Okay, and I want you to be able to see this a little better. And then I know, and I know you're aware of this as well, that if I do find the inverse, when I graph it, it's going to reflect across the line y equals x. So now, this is the tricky part. Here's the inverse, y equals, and if you look back here, this is why it's a little tricky, it's brand new to us. It's log base 2 of x. That's how we say this, log base, in this case it's 2, of whatever number's in back x, log base 2 of x. So how do we plug this in? Well, if we come over here to the word functions, and we go to miscellaneous, you're going to find log with a little tiny subscript a. That subscript is where I put the 2. I use the arrows to go in back. And now I can see if I fold it along this black line, the purple would reflect straight across and would actually map right on here to the red. Now let's just make sure that we did this correctly. So what I'm going to do right now is I'm going to choose a couple of these. This is from the original. I'm going to choose a couple from the original, and then I'm going to flip-flop them. So for instance, 1, 2, and 2, 1. And if this is on the original and this is on the inverse, if this is on the original and this is on the inverse, I've just proved myself 2 different ways that I did the math correct. They're inverses of one another. So I'm going to do 1, 2. No reason why I chose that particular one. And if I map its inverse, it should be 2, 1. And I can see they're both on the line. If these points would not be on the lines that were graphed, it tells me that my inverse that I created was wrong. 2, 4. Again, I can see that it's on the line. And lastly, 4, 2. Okay, so I've proved myself it works. And you may be seeing like, yeah, I understand how it works, but let's go back to this whole log thing. That's the confusing part. Well, that's the lesson for today, is what are logs and how can they help us? Once again, logs are just another way to rewrite exponents, and the sole reason we learn them is so that when you are going to solve for an exponent in which there's a variable there, that's the reason we learn logs. Now, how did this thing just appear to be 1? Let's talk about that before we jump into logs. How did this thing just turn into a 1? Well, this is what this means. It means if you take this number and you raise it to some exponent, you're going to get an answer of 2. So what's the only number you can raise 2 to and you get 2? 2 to the first is 2. That's how this whole thing became 1, and that's what we're going to jump into right now. The first 2 tasks of today will come in very important at the very end of this lesson when we're going to put everything together. So the first 2 tasks are exactly opposite of one another. Each one of these, if you look, each one of these is an equation in which the left side equals the right. That's how equation works, left side equals the right. And each one of these has a log. Now we want to rewrite it so it no longer has logs and it's in what's called exponential form. Exponential form. Now exponential form looks like this. Again, if you are somebody who's struggling today, you may want to write down just the basics of today and go back and watch this compressed video in YouTube and rewrite it again. But exponential form looks like this again. We have a base, we have an exponent, and we have an answer. So I'm going to write this is your base, this is your exponent, and this is your answer. So I'm going to take this and I'm going to put it into this form every single time. So I'll do this for the first one. There's going to be a base, an exponent, and an answer. Now the base remains the same. Whatever that subscript is, that's right behind the log is always the base. So the base here is 2, 3, 1/4, 11, 64, and 0.25. Your base will always be positive, so that's another thing to write down. Your base is always positive. So I put a 2 now, and it no longer is a subscript, it's the base of this exponential, a really exponential expression. We're going to make it into an equation in just a second. So the subscript 2 now becomes a big 2. And whatever is right behind the subscript is actually the answer. See how it's the answer. This is the answer. So on the opposite side, I'm going to write 1/8. Now your answer can be positive, negative, or 0. There's no limits. This particular one happens to be positive. So there is your base, this is the answer, and now this is always the exponent. So up here I'm going to write in -3. This is the exponent when I switch it into a different form. This is the answer, and this is the base. Now, we're not going to have to do this every single time, but if this is seeming really foreign to you right now, I do want to show you how this makes sense, okay? Remember, there's two purposes of logs. One is that they help us just to another way, an alternative way to write exponents. And two, the main reason we learn them is when we're trying to solve for a variable, if it's in the exponent positions, we need logs to do that. So this is just another way to write this. Okay, you ready? Let's see, does this make sense? It does, but let me show you how. Forget about this being a negative like we talked about last week. Let's just pretend this is, if I could cover that up, let's pretend it is 2 to the positive 3. Okay, pretend that's 2 to the positive 3. So I go, okay, here's 2 to the third. So to the first, to second, okay. So 2 to the third is 8. I agree, 2 to the third is 8, but there's a negative, which means it's not happy, it goes to the bottom. Do you have to go back and check each one of these to see that it works? No. This equation already says it works. We are simply practicing rewriting it. So here, I start with the base, I rewrite the base, and I always jump across the equal sign, and this is your exponent. So 2 to the fourth, the answer is right behind, is 81. Over here, start always with the base. 1/4, jump across the equal sign, grab the negative, or grab in this case the negative 2, which is the exponent, and come back to the answer. Coming back up here, I have one more statement again. Remember the base here, in this position, your base is always positive, okay? Your base is always positive in this position, so I'm going to draw a little arrow. Your base is always positive, and your answer, and the answer, which is right here, they're always positive, which means you're not going to see something like this. If I give you an example, you're not going to see log of -2 and -3, I don't know, 1/8. That's not true. This will never be negative, and this will be negative. But this answer could be 0, positive, or negative. Okay, this is applying to logarithmic form. Okay, so I've just done 3 of these. Again, base raised to the opposite equals this answer. Base raised to the opposite equals this answer. Base raised to the opposite equals this answer. I would like you to do these 3. I'm going to give you 30 seconds. I'll give you a little bit of a head start. I'll zoom it in for you. And let's see if you can do this. Ready? Begin. Please do me a favor. I'm asking for everybody's participation. I do not want you to unmute because I am filming this. Please do me a favor and go into the chat right now. Go into the chat, not unmute yourself. And can you give me a 1 through 5 on how well you understood right now? Just writing it from log to exponential form, log to exponential. Give me a 1 through 5, please, right now. Okay. Thank you for everybody who's participating in me and giving me that feedback. We will have more practice here as we move forward. Now we're going to do just the opposite. Notice that none of these have logs. So I'm going to do just the opposite in setting it up. So if I would come over here, I'm now going to have a log, a base, an answer. Okay, so it's like this. Just like this, okay? Now remember, this was your base, this is the exponent, and this is the answer. Okay, the same thing applies. So now I want to rewrite it in that form. So log, the base remains the same, but I have to write it really small. So log base 5, it's a subscript. The exponent was on the opposite side, and the answer was right behind it. 5 to raise to the second, so 5 squared equals 25. That makes sense. The base remains small, the exponent is on the opposite side, and the answer is right behind it. 4 to the third is 64. This is not 4 times 3. This is 4 times 4 times 4. 3 times is 64. And last one here, log subscript of 2/5. The exponent is on the opposite side, and the answer is right behind it. Now, just to go over this once again, this base with in log form will always, always be positive. And the number behind it, the answer, will always be positive. They may be fractions, they may be whole numbers, but they will be positive. The number in back can be 0, negative, or positive. I'd like you to try these three. I'll give you another 30 seconds. The answers for B, D, and F are shown here. We're going to just take a practice assessment to see where you are. So here's the first one. So on your paper, you will not be sharing this with me. On your paper, please write down, is this currently in exponential form, or is this currently in logarithmic form? On your paper, not in the chat, please write down, is this in exponential form, or is this currently in logarithmic form? Correct answer is this is in exponential form. For those who are feeling a little confused, when it's in logarithmic form, you will literally see log as a word in it. Okay? Now I want you to rewrite this in an equivalent logarithmic form. Go ahead. The base remains the same. So base, I just have to rewrite it as a subscript. The exponent always goes on the opposite side. And the answer, in this case 1 over 125, goes right behind it. Can you go into the chat right now, a thumbs up or thumbs down if 1, you were able to recognize this was already in exponential form, and 2, you were able to rewrite it correctly in logarithmic form. Thumbs up, thumbs down. Thank you for your honest responses. Okay, here we go with the next one. Please rewrite this in exponential form. This is logarithmic form. Please rewrite this in exponential form. Two remains the base, it's just larger. The exponent's always on the opposite, and the answer is 1 over 16. So we've done two learning objectives so far. The first learning objective was, what are log functions? And we looked at how we went from exponential to logs and how they're inverses of one another. We looked at that in two different ways. We looked how the domain and range were flipped, where they're inverses of one another. They were right vice versa. We also looked about how do we mathematically find the inverse, because that's really the reason we learn logs. Yes, there's another way to write exponents, but the real reason is when you're solving and the variable is in the exponent positions, you have to have a log. Okay, we're going to jump down. This was task number 2, going from exponential to log and log to exponential. And now task number 3. Task number 3 is there a way for us to evaluate this? If logs are just another way to write exponents, is there a way to evaluate it in our head sometimes, or sometimes can we even use a calculator, like a Desmos calculator, to do that? So the very first one I'm going to do using either the table or mental math. So what does this mean? So when you don't see an equal sign, you can put equals question mark if that helps you. So I'm going to start by rewriting this in exponential form. So here's my base, 2. The exponent, I don't know what it is, so I can put an x, I'm going to put a little question mark, and it equals 64. So in my mind, I'm going, okay, 2 to what power equals 64? So I'm going to come over here to my table. 2 to the first, the second, the third, the fourth, the fifth, the sixth. Oh, 2 to the sixth is 64. That means this answer, 2 to the sixth is 64. That means this answer is 6. I'm going to do one more, and then I'm going to go back to showing you how you can use Desmos as a way to do this. So here, I'm going to write 1 over 2. Okay, so base raised to the exponent, I don't know what the exponent is, equals 4. Now there's really, I'm going to write this on a different piece of paper. This often causes problems for students. So the way I want you to think of this is that we're going to cover up the 1, and I'm just going to go 2 raised to the what is 4. 2 raised to the 2 to the second is 4. So I know this should be a 2. So I have 1 over 2, and this should be a 2. But if I square 1, 1 times 1 is 1, and if I square 2, 2 times 2 is 4, but I don't want 1/4. I want it flipped so that 4 is on top and hidden 1 is on the bottom. So in order to do that, I need to have a negative 2. So 1/2 raised to the negative 2, remember that negative exponent means we flip it, becomes 4 over 1. This answer should be negative 2. Now I'm going to show you how using Desmos can easily allow us to get those answers. So this third learning objective is, how can you evaluate it? I'm going to give you something simpler first. Let's say you were just being introduced to exponents and you wanted to know, like, how can I tell what 2 to the 4th is? How can I tell what 2 to the 4th is? Well, instead of going 2 times 2 is 4, times 2 is 8, times 2 is 16, which totally works, or you could look at a table, here's another way. You would just use this as a calculator. So we're going to do the same thing now. I'm going to show you how, if mental math wasn't your thing, I'm going to come back here just to show you what I'm going to do here. I am going to first show you how I can plug this in to get an answer of 6, and I can plug this in to get an answer of negative 2. So it was log, I've got to go over to functions, find miscellaneous, and go to log base A. Now I'm changing that A for the first one into a 2. Remember, I got an answer of 6, and we can see it evaluates to 6. I'm going to leave it there to kind of be lazy, and now I'm going to change it. 1/2 or 0.5 and 4. This is read log base 0.5 of 4. Log base 1/2 of 4. Log base 2 of 64. Log base 0.6 of 25 over 9. Okay, so let's evaluate that. Again, I'm going to change this to a 1/2. Even easier to write is 0.5. And inside was 4. And we can see the answer is 2. Let's go to one that looks a lot more complicated, something we probably wouldn't do in our head. So if I look at any of the ones here, like the ones that look really confusing to me is this. Like, I'm like, what is this? So I'm going to plug that in to see what kind of answer we get. Log base 1.25 of 125 over 64. How do we do that? So again, if I never had this up here, I would go to functions. I would go to log base A. Notice there's just a log. We'll talk about that one later on, log base A. And now this was 1.25, and inside the parentheses was 125 divided by 64. And the answer is 3. Well, that's a nice answer. Okay, so all of these gave us nice answers. If we went through every single one, or I gave you time, it all gives us a nice answer. It may be a fraction, It may be just a nice integer answer, like a 6, a -2, a 1/2, those kind of answers. They're all nice answers. But down here, it says, hey, some of these answers may be nice and some of them may be ugly. They may be irrational, an ongoing decimal. And if that's the case, round to the nearest thousands. So, okay, all this looks easy, except for what's different about these 6 compared to the 6 above is 2 of them, they don't have bases. See how I have a base, a base, a base, a base. This doesn't have a base and this doesn't have a base. When you don't see a base, it's called a common logarithm. Our numerical system is based on tens. Think of this really quick. We go 1 through 10, and then we really repeat that. 11 through 20, we're counting by 10 again, right? We're counting by 10 again, and it goes on, right? It's continuously counting by 10. So a common log means that this number doesn't have to be written. So regardless of what number's in back, this number down here doesn't have to be written. It's just known that it's 10. So when you don't see a base here or a base here, for example, in A and D, there really is a hidden 10. In this next part, so this is still a part of task number 3, is can you evaluate a log expression? Either you can do it with mental math or you can use Desmos as a calculator. So let's plug this in. I'm going to do log 10 or log base 10 of 8. Log base 10 of 8. So I come up here, I change this into a 10, I go back, make it an 8, and now, oh, that is an ugly answer. So if I could zoom this in, we're asked to round it to the nearest thousand. So, okay, here's tens, there's hundredth, this is the 3 is the thousand. So when you decide, well, do I keep it at 0.903 or do I round it up? You sneak back here and you look at the number right behind it. If it's 5 or above, you round up. Because it's not 5 or above, we're going to say approximately 0.903. That's rounded to the nearest thousands. Now, what if you evaluate and you just get a nice simple answer, like there's no extra decimals? Then you don't have to worry about rounding. So I'll do the next one. So that one is log base 0.2, and the number in back was 15,625. Oops, excuse me, 625. We get a nice integer answer of -6. Sometimes students in the past have asked, like, well, what do we round it to if there's no decimals? You don't have to round. That's just an answer. There's no rounding. This means exact answer. This means I rounded it. Can you do me a favor right now? And can you go back into the chat for me? And by the way, I really appreciate when you're giving me honest feedback. It's okay if it's a 1 or 2. This particular task, this third task, is your comfort level with just simply evaluating whether you use mental math or you use the Desmos calculator to get an answer. 1 through 5, please. Thank you for the feedback. Now, before I move on to the next one, we got to talk about a couple things here. What does this mean? Remember how I spoke that when we were solving the very first task and I was showing you about inverse functions, we had something like this. And I showed you that this portion really means 2 raised to what power equals 2? 2 to the first. So this thing equates to 1, and then I was able to bring down the exponent. What we're going to do here is we're going to use what's called inverse properties, and the whole goal is there a way to simplify these? Is there a way to simplify this? Okay? So I'm going to show you how this actually equals 4 right now. I'm going to show you how this equals 4. If I only look at this portion, I see log base 9 of 9. When these are exactly the same, they don't wipe out and it's magically gone. It actually simplifies to a 1, and you bring down whatever exponent was there. 1 times 4 is 4. C and E are just like A. C and E are just like A. The difference is A was really nice. It was already a 9 and a 9 back to back. Here I have a 3 and 81, and your first thought is they're not the same. I can't do that. Or remember, here's a hidden 10 down below. It's a common log. So a 10 and a 1,000, they're not the same. But we can rewrite it so they're the same. So if I look at the 3's, I'm going to go, is there a way to rewrite 81 with a base 3? So here's my 3's. I'm going to keep going until I find 81. Oh, okay. So 81 can be written as 3 to the 4th. So log base 3 of 3 to the 4th. Now, why would I take time to do that? Because now this problem looks just like this in many ways. Log base 3 and 3, when you evaluate that part of the expression, it simplifies to a 1. Then you get to bring down the 4. 1 times 4 is 4. And I'm so sorry here. I forgot there's also an x, a really small x. I need to attach that x as well. Okay, this next one, I'm going to rewrite 1,000 with a base of 10. So I find 10 and I realize that 1,000 is 10 cubed. So log base 10. Again, this is 10 cubed, and there's that x that I forgot up above. Okay, log base 10 of 10 turns into a 1, and I have 1 times 3 times x, which is 3x. We're going to have you try one next. Please simplify this expression. Okay, so how can we do this? So again, I want to rewrite this. If I can't rewrite this with a base 5, then there's nothing I can do. So I come over here and I find the 5's and I go, oh, okay, 125. I can rewrite 125 as 5 cubed. Log base 5 of 5, log base 5 of 5 does not just eliminate itself. It doesn't just disappear. It turns into a 1. I have 1 times 3 times 7x. 1 times 3 times 7x is 21x. Can you please give me very honest feedback? Before you do it, please listen to the instructions. A smiley face is either I got it right or I see my mistake when I understand it. A frowning face is I'm still really confused about this type of problem. I know I may never be able to get 100% of students' understanding until you have a chance to practice, but we want the majority of you to feel confident. Okay, we're going to look at the next type of problems. Now, the next type of problems, again, our whole goal with these problems was, is there a way that I can simplify this problem? Without doing much work, can I simplify the problem? And that's what we're going to do here. Okay, that's what we're going to do here. Now, what's the difference about this problem and these problems? Here, notice that in each one of these positions, the log is up top. Again, notice that the log is up top, and not only that, notice that the bases are exactly the same. The base of the exponent is the same as the base of the log up top. Okay, this is a 10. You may be saying that they don't have the same, but remember, I don't see a base here. There's no subscripts. That's a hidden. It's called a common log. So again, 10 and 10. And 7 and 7. What do we do when that's the case? When that's the case, these actually do the exact same thing. Just like we did over here, these actually evaluate to a 1, and then you get to bring down everything else that's there. So if I distribute this one, it doesn't do anything. 1 times 5x is 5x, 1 times 3 is 3. This simplifies to the expression 5x plus 3. Again, there's a hidden 10 here as the base, log base 10 of 3, and then I have 1 times a 3 and back, which simplifies to 3. Here, they're going to give me a 7 and log base 7. Those are going to eliminate into a 1, or simplify into a 1, and then I get to bring down the 2x, and 1 times 2x is 2x. Let's try one, please. Okay, go ahead please and simplify that expression. Put your final answer into the chat. Please type in your final answer. And if somebody's already put the answer in front of you, you're welcome to like their answer. If you don't see the answer you achieved, if you do not see the answer you achieved, you can type it in yourself. All right, so we're going to go on to part 2 of today's lesson, and let's just recap what we've gone over so far. If we work backwards, here we go. Okay, so this is becoming really important as we move into the second part of today's lesson. So, the last thing we just did, this last task was, can you simplify? So these 3 were the same as these 3 in terms of the operation. So can you simplify? Up above was, can you use Desmos or mental math to simply evaluate a log expression? Prior to that, you were asked to rewrite from log to exponential or exponential to log. And then we started the class with just talking about what are logs and why do we use them. All right, so we're on to the last part, which is part 2. It consists of 8 problems, and I don't think we'll end up doing all 8. Let me cover some of this up here. Okay. So for some of this, I'm going to try a problem, and then I will have you try a similar one, and you can provide me with the feedback. So in this problem, we're simply asked to solve for x. Now, the first thing to do is ask yourself, is this log form or is this exponential form? I'm talking about problem A. This is in log form. How do I know that? Because I see a log. So the first thing I would suggest you try to do is try to rewrite it in exponential. Remember, exponential is there's a base, an exponent, and an answer. So now you have to think, where does the 4, the x, and the 5 halves go? 4 is the base still. The exponent is always on the opposite side, so 5 halves, and the answer is right behind it. Our whole goal is to solve for x. Now, could I try to do this in my mind? Absolutely. Or we could jump right over to Desmos. 4 raised to the 5 halves. The answer is 32. And I get to write x equals 32. Your next part may be, is that all I have to do, miss? Yeah, that's all you have to do for that particular problem. I would like you, using the skills we just learned about simplifying, to attempt to do, it may not be the exact same as number 1, but I think based on the feedback I received from the last task, you can do okay here. Let's see what you can do with C. I'm only going to give you 30 seconds. Don't feel bad if you're not done yet. But if you do get done before I ask everybody to stop, please put your answer into the chat. If you see it from somebody else, you can just like that so I can see how many people are getting that. If you don't see your answer, you can place it into the chat. Begin. Okay, here we go. So log base 16 and 16, remember, they don't just disappear. It simplifies to a 1. And I bring down the 2x minus 1. Now when I distribute a 1 here, it doesn't change anything. I still have 2x minus 1 equals 11. I'm going to add 1 to the opposite side. So I'm going to add 1 over to get 12. And then I'm going to divide by 2, and I get x equals 6. Well, let's check here. We know this simplifies to 1. 2 times 6 is 12. 12 minus 1 is 11. 11 equals 11. Please put an E into the chat if you would like me to, re-explain that problem. Waiting to see if anybody put an E in there. Okay, we're going to move on. Now this is very similar to what we just went over in the last task. I'm going to give you 30 seconds, exact same thing. When you get an answer, put it in. If you see your answer already there, you can just like it instead of typing it in. 30 seconds begin. Okay, I'm going to try it here. So log base 8 and 8, okay, that turns into a 1, and I have 3x equals 15. Divide by 3, 15 divided by 3 is 5. I just want to make sure this is right. I know this equals 1. 3 times 5 is 15. 15 equals 15. Put an E in the chat if you'd like me to re-explain. All right, let's see what you can do. This is like problem number 1 that I showed you how to do. This is in logarithmic form. I'm going to give you 30 seconds to begin. The base remains 1/4, the exponent is -5/2, and the answer is in back. So I'm going to go over to Desmos, and in this position I'm going to put a 1/4. Also, I can write 1/4 as 0.25, and I'm going to raise it to the -5/2 to get an answer of 32. An answer of 32. So x equals 32 would be my answer. Please put an E. Please put an E if you'd like me to re-explain how I did that. Please put an E. Okay, don't see any E's. We're going to go on to the very last thing for today, and that is how do we solve? Oh, okay, how do we solve? Well, there's a couple things to know about. It kind of relates to this. If you guys could look up here really quick. Back up here if you happen to be in Desmos still. If I gave you something like this, completely making this up. Okay, so I just made that up. I don't even know that that works. And I said, how do we solve this? Well, when we got back from fall break and we talked about solving rational equations, I said, if you can find the bottom to be the same. So we talked about what is the least common denominator. This would be 4x. I need I need a 2. And a 4, so now I have 4, 4, and 4, and they all need to have x. There's an x, and here's an x and x. So 2x, 2x, x, x, and 4 and 4. Now when that happens, I had 4x, 4x, 4x. I'd wipe out the bottom, and I only had to worry about the top. That same type of concept is going to occur here. See how I have a log base 5 and a log base 5 on opposite sides of the equation? Log base 2, opposite sides. Down here it's log base 7s and log base 11s. We don't see anything extra like a +3 or a -7, anything that's randomly behind it that's not already in parentheses. When this happens, you get to literally just wipe this out and you get to solve the equation. So this would be x squared minus 2 equals x, and this would be x squared minus 15 equals 2x. But before we do that, we have to talk one more time. Remember about logs? I spoke today about this being the base, this being the answer, and this being the exponent. And I said these two will always be, these particular two will always be positive. The base and the answer will always be positive. The exponent can be positive, it can be negative, or it can be equal to 0. Keep that in mind today. So when it says check your answers, it means that there could be extraneous solutions, there could be, and we have to know that rule about what can be positive and what can be negative. Okay. So we have right now an exponential equation. I'm going to move the x over. When it moves over, it becomes negative, and now there's nothing left over here. So remember I said exponential, I meant to say quadratic equation. We can solve by factoring sometimes. We can always solve by completing the square or by quadratic formula. So this multiplies to equal -2 and combines to equal -1. So x, let's see, can I do this? X minus 2 and x plus 1. Yes, they multiply, and yes, they combine. That means one answer, I believe, is 2, and one answer, I believe, is -1. Now let's check and see. Now just because it's negative doesn't mean it's extraneous. We're going to take this and plug this in. All I care about is after I substituted this particular number of 2, does this region equal a positive number? If it does, it means I'm not breaking any math rules. Remember, the numbers that are the base or directly behind the base have to be positive. Okay, 2 squared 2 squared is 4. 4 minus 2 is 2. It's positive. Okay, great. Plug in a 2. It's positive. That means this works. One answer is 2. Now let's try negative 1. Negative 1 squared is positive 1, but 1 subtract 2. 1 subtract 2 is a negative 1. You can't have a negative back here. That means this is extraneous. Okay, I'd like you to solve this on your own and then check by plugging it back in what would be the answer to this problem. I'm going to give you 30 seconds. Begin. $25 minus 15 is 10. It's a positive number. Good. 2 times 5 is 10. It's a positive number. That works. Negative 3 squared. So negative 3 squared is 9. 9 minus 15 is a negative number. Just like 2 times negative 3 is negative. Can't have a negative behind it. Correct answer is 5. Negative 3 is an extraneous solution. Can I have right now a 1 through 5 on how well you understood B? Even if you didn't have a chance to finish, when you look at my work, can you please give me feedback on how well you feel about or how comfortable you are with doing problems like B, please? Again, asking for your feedback right now so I know. How comfortable are you with doing problems like B? Thank you. Okay, the exact same thing right here. I want you to attempt to do D, and I'm going to give you right now a minute and a half. Ready? Begin. D. Sometimes students, and as continue to work, they don't know when they get to this point, like, do I move things to the left or to the right? There's no rules that say you have to move it one way or the other. I generally find that myself and students make less mistakes when you move everything to the side with the x squared. When this moves across, it's negative. When this moves across, it's positive. I'll let you continue working. Negative 2 and negative 1 multiply to give you 2 and combine to give us negative 3. So x equals 2 and x equals 1. Now let's see, are they both the answers? Only one. So I'm going to start with 2. 3 times 2. 3 times 2 is 6. 6 minus 1 is 5. It's positive. 2 squared. 2 squared is 4. 4 times 2 is 8. It's positive. Well, let's look at that one more time. If I plug in 2. 3 times 2 is 6. 3 times 2 is 6. 6 minus 1 is 5. I get a 5 here. I plug in here, 2 squared is 4, 4 times 2 is 8. Okay, that's what I get here. Now let's plug in a 1. I'm a little concerned, see how the left side doesn't equal the right? If I plug this in and I evaluate this with a common base of 10 and I evaluate these, I know they're not going to be exactly the same. Straighting solution, let's try 1. 3 times 1 is 3. 3 minus 1 is 2. I meant to say base 11, excuse me.
Liz, you forgot to do bottom stop, no?
I did, didn't I? Thank you so much. I forgot the stuff that I continuously tell you guys not to forget, didn't I? Let's go back here. Absolutely. Thank you for finding that mistake. So here we go. This is going to be positive 1, and this is going to be positive 1/2. So before I check them, can you let me know right now if you see any other mistakes? Anybody see anything else? Thank you so much for catching that. Okay, let's try 1 now. So when I substitute in a 1, 3 times 1, again 3 times 1 is 3. 3 minus 1 is 2. So I have right over here log base 11, 2. And then I substitute over here, 1 squared is 1. 1 times 2 is 2. So I believe that 1 is an answer. Let's try 1/2. So half of 3. What is half of 3? Half of 3 is 1.5. And 1.5 minus 1 is 0.5. So when I plug in this, I end up with log base 11 of 0.5. Let's check on the other side. I want to take 0.5 and squared and then take it times 2. 0.5 and squared and take it times 2. So if I come over here and I do 0.5 and I square it, and now I take that times 2, I get 0.5 again. So in this particular problem, whether I use 1 or I use 1/2, when I substitute, both the left side will equal the right side. So both of these happen to be the answer for this last one.